Я вот тоже здесь.
То есть у нас не все с тобой красиво.
When yesterday I introduced Professor Durlauf at Moscow State University, I did it in Russian, but we had a translator then, so he knew what I'm saying. So I immediately will now switch to Russian without the translation, so not know what I'm saying. And that's sorry for the foreign audience, I'll do it in Russian. Я очень рад приветствовать профессора Дурлауфа, нашего гостя нашего центра по изучению разнообразия, многообразия в Российской экономической школе. И дайте мне немножко рассказать, одну минутку рассказать про Стивена. Он закончил, как говорят, Harvard и PhD в Йеле, и уже 20 лет является профессором в Висконсин, он остался на поле СМК. Но что интересно, что Стивен является именным профессором Висконсин, только именным профессором, тройным именным профессором. Профессор, три на самом деле, три студента, Висконсин, Эрол, Кришченсен, Виллас, Research Chair. Все это действительно выдающееся достижение, он является членом Американской академии наук и искусств, ну и много различных других вещей, которые можно было рассказать. Но я все-таки скажу минуточку, что чем удивляет действительности, это его широта, его интересов. Во время, когда мы так специализируемся, каждый сидит в своем уголке и занимается чем-то своим, он занимается выдающими достижениями по эконометрике, и по микро, и по макро, и по теории, вообще по всему диапазону. Вчера мы узнали, кстати, после лекции, что я думал, что когда он говорит о неравенстве, он говорил о экономическом неравенстве. Вчера выяснилось, что есть и расовое неравенство, и вещи, которыми он занимается, не только экономика, это философия, политика, социология, и все широта этих вещей. Так что это его первый визит в Москву и Россию. Конечно, мы сомневаемся, что он приедет еще раз, будет сотрудничать, и на самом деле очень рады, что он приехал, нашел время и в лекции прочитал, с нами видеться. Очень рад вам приветствовать.
Thank you, and actually I know pretty much what you said because I heard the translation yesterday. I could map up a large number of words. There was no escape. Thank you all for coming, and thank you for an absolutely delightful visit here. Like you said, that this is my last chance to speak here because I've had such a delightful time, and I've learned immense amount, and I'm grateful. That said, I'm a little bit worried you'll be bored with this talk, and I mean that at two levels. One, of course, the material might not be so interesting, but second, my understanding, this is really targeted towards the students, and so I think the practicing economists here will say that this will all be pretty repetitive. What I wanted to do in this talk was to describe applications of a certain branch of mathematics, statistical mechanics, to modeling economic behavior. And I wanted to do that for two reasons. One, introspectively, and maybe immodestly, this has been my interest for almost 20 years now. And a second reason is that the mathematics that I've come to work with was all developed here. And so there's an intellectual depth that I very much feel. And of course, the third reason, the most important one, is I think that the surface has scarcely been scratched in the use of these tools in modeling various socioeconomic environments. And just there's an enormous number of interesting research questions which are outstanding. And so what I wanted to do is give a brief overview of what these tools are, give you some sense of how they at least have been applied, and more narrowly how I've applied them, and finally give some indications of where I see some open problems. And in fact, I'll tell you about a paper I'm currently writing with two graduate students, and I won't say we're stuck, but where we are. By way of background, as I've said in other lectures, the reason for wanting to use the tools is not an end in themselves, of course, but rather that they're going to be a language that facilitates the study of certain substantive questions, and the questions I'm personally motivated by tend to involve inequality. And beyond that, I'm interested in these social determinants of inequality, and it turns out that these tools are very conducive to formal modeling of ideas that appear in this literature. Now, what I mean by that is that in thinking about how social influences affect individuals, there's really two types of questions to ask. The first is how one would formulate conditional on a social environment, interdependencies in decisions, and the subsequent choices, not just of an individual, but the entire population. That, as I'll argue, there's a sense in which statistical mechanics models actually do exactly the same thing. They provide a powerful formal language that we'll see. The second point, of course, is that it isn't enough to just say conditional on social structure, there's an outcome, but rather one might want to also model the evolution of the social structure or the determinants of the social structure. And that's going to turn out to have a statistical mechanical analog as well. And so, in fact, methods from the relevant mathematics literature apply to both sides of the inequality social interactions literature, both what happens conditional in the structure and how does the structure emerge. The idea of the emergence of structure is often referred to as social networks theory. It's maybe the big application now. But in fact, those models as mathematical objects fall into the same template. And so when I said, once what I'm currently working on, is how you stick them together. In other words, a model in which you both have social structure and the subsequent choices co-evolving. Now, in thinking about interdependencies of decisions and the effects on behaviors, what are the sorts of things we'll ultimately be looking for? One of them, of course, is to specify decision problems that are, in some sense, well posed. In other words, that there's a well-posed notion of preferences, constraints, and belief formation from which individual decision rules come. And the way that I'm going to set things up will be that when I talk about individual decisions, and of course there'll be tautologies in the sense that they're the solutions to some maximization problem. Okay. The theory has no content in that sense. It says by definition you observe behaviors, they maximize something. All the interesting activity is what the something is. But what's going to make the models linked to a particular area of probability theory is the way I write the problems will be paying close attention to the notion that when I talk about or describe my behavior, that has explicitly a probabilistic description. In other words, that you can say, conditional on the things that are observable about me, this is the probability I do one thing or do something else. So in a binary choice or discrete choice context, I would have to destroy the technology, but let's see if we can robust. Okay. I would actually have probability masses on the different choices, and otherwise I would simply have standard continuous density. So the point is, this is just elementary economics in the sense that there's a decision that's being made, but I'm going to be careful in modeling the decision or modeling the environment in such a way that at the end I think of the decisions of the individuals, or I express them as conditional probability statements. One advantage of that is that it creates a natural segue between empirical work and theoretical work. Okay, so in other words, there's many ways to write economic theories down. And I'm willing, again, this is my philosophy as it were, I'm willing to make many sacrifices in terms of the generality of the theory if at the end it's providing these conditional probability statements. The reason for that is that what in this theoretical model is called the conditional probability of an individual's behavior, an econometrician gets to call the conditional probability from which a likelihood function will be constructed and parameters can be estimated. So one advantage of trying to sort of force the decision problems into a particular probabilistic language is that there's a natural transition from the theory to the econometrics. And so anything I call an equilibrium in the theory model is also going to be a likelihood function if I'm going to do empirical work. Okay, so that's idea number one. Idea number two is that in thinking about behaviors of phenomena, so if I say I'm interested in the rate of high school graduation in a population of students, or I'm interested in the rate of commission of crime among a group of teenage males. I don't know what it's like in the Soviet Union, a very bad slip, in the Russian Federation, but in the United States you won't be shocked to hear it's males commit almost all crime. So that would be the natural population. The point's the following. When I ask questions like that, I'm asking about statistical regularities, or I'm asking about moments of a distribution. The point's the following, that what the microstructure is going to be is nothing more than you make a decision, I make a decision, collectively there are a bunch of conditional probability statements. Interdependences mean that I can't just say that's the solution, I have to account for those interdependences. And so the notion of an equilibrium here is a joint probability description of all the choices in a population that is compatible with the conditional probability statements that represented the optimal choices for each individual. All right? And what that then does is kind of change the mathematical. You can see now the existence problem becomes a mathematical problem. When does a set of conditional probability measures generate a joint probability measure, an unconditional probability measure? Okay, that's an existence problem. To talk about multiple equilibria in these environments, I would ask, does there exist more than one unconditional probability measure that generates the same conditional probability measures? Why would I want to do that? Because one of the important ideas in this approach is the possibility of multiple self-consistent behaviors of groups of people. So one can have two groups of people in which their microstructures look identical, yet one is exhibiting, let's say, high rates of crime, another low rates of crime. Put differently, one population, identical observables, has a high rate of graduation, completion of high school, another a low rate. Okay, and so the point is that there's always going to be this parallel between a mathematical property of the systems of probabilities and kind of a substantive economic questions such as existence and multiplicity. All right, and so again, I don't want to. There's many ways in which one can go about modeling populations of interacting agents, and this happens to be a set of tools that I've found useful, and I think have a lot of potential. So that's kind of a long-winded background. Okay. So, in referring to statistical mechanics, this is very informal. It's a branch of physics, shock of shocks, which studies essentially aggregate properties of large populations of objects. That's all it is. Okay? And in fact, the mathematics literature has gone far beyond the initial physical models that motivated the development of these types of models. And kind of the classic example of statistical mechanics was to understand how magnets could appear in nature. And so a magnet, metaphorically, roughly speaking, is a chunk of metal, a piece of metal in which the atoms are either spinning in a way that in the aggregate are up on average or down on average. And the degree of, you are all much better trained in math and physics than I am, so the more the tipping, as it were, towards one or the other, the more intense the magnet is. All right. So that's, and in fact, the mathematics emerged from this this question, which is how magnets could arise in nature. And 100 years ago or so, this was an outstanding question in physics. The reason essentially was the following, and that is, okay, a piece of metal is a very large number of atoms, and there were physical reasons why the probability that an atom was given atom spinning up or down, there was no way to there was no bias one way or the other. So it's got an x ante 0.5. So the question was, how could it be that this large collection of atoms tilted one way or the other? Law of large numbers sounds like it ought to kick in pretty fast with the number of atoms in a piece of metal, and so if each atom had an x ante probability of 0.5 of up or down, that was the paradox. The resolution was to argue that the law of large numbers didn't apply because dependences between the spins were not accounted for. And so the statistical mechanics of magnets, in essence, works in the following way, which is specifying conditional probabilities of one spin given other spins in the system, associates with those conditional probabilities a parameter that says something about the intensity of the condition of the relationship, the strength of the conditioning, and the fundamental result was that system can tip, and so it can tip either with positive, up or down spins. But the upshot was it was the interdependence of the probabilities of the outcomes that generated this phenomena called magnetization. Okay, so that's where it gives you a hint as to why there's going to be something about multiple equilibria when we use this to talk about the socioeconomic analogs of these types of physical systems. So is everybody with me? Now, interestingly enough, in the case of magnets, the classical model is called an Ising model, and the way that that works is named after a physicist by the name of Ising. And you can sort of think about, and the way that you idealize the material is you say, here's a given atom, and I can ask what's the probability it spins up or spins down, given, in this case, its nearest neighbors. So I could ask what's probably this one spins given those four, so on and so forth. Okay, now the reason I put this on the table is you can see that, I'll put it on the screen, that's a one-dimensional model. I could think here's a population of objects, they could, in this case atoms, one-dimensional lattice, in which this object depends on those two, so the conditional probability, this is just a function of those two, and that would be true for every element. That's a two-side Markov chain. And so the history of the Ising model, the great development of the foundations of statistical mechanics, is important for the students to know. Ising was a graduate student of a distinguished German physicist by the name of Lenz, and Lenz proposed to him as a thesis, why don't you see whether or not a magnet can emerge from interdependences in spins. And so that's what Ising worked on, and what he did was he wrote down a one-dimensional system, and it's just a two-sided Markov chain. Every two-sided Markov chain is mathematically equivalent to a one-sided Markov chain. And by symmetry, it meant that this had to be the probabilities of the elements of the system. That's it. And so if I said, you tell me how many invariant measures there are, I think you tell me there's one. It's a half. So in other words, this model could not produce the magnet because on average, half of the elements had to be spinning up and half are down. So Ising published this result and became a liberal arts professor in rural Iowa, and actually only died about 10 years ago. He lived to an extremely old age. Then about 25 years later, another physicist, Rudolf Peierls, went back to the Ising model, and he said, well, what if I do it in 2 dimensions? So the idea was that Ising had a one-dimensional analysis. Peierls did a 2-dimensional. And so, again, had the spins, you depend on nearest neighbors, but they depended in those 2 dimensions. And the astonishing result was, even though a magnet was impossible in the one-dimensional system, it could exist in the 2-dimensional system. Now, why is that? If you think about the Markov chain here, intuitively, the only way that the realization here can affect this element is this affects this, affects this, affects this, affects this. In other words, there's a geometric decline except for the degenerate case when the probabilities on the diagonal are ones. But what's happening in the 2-dimensional system? This element can affect this, can affect this, but it also could affect this, could affect this, could affect this, could affect this. The serious point is the following, is that once the dimension of the system changed, the number of paths that connected the elements of the system actually grew as the distance between any two elements increased. And so even though along each path dependence attenuated, there were more paths in which the connections occurred. And so that's the very big result, is that there's actually a dimension dependence. And that tells us something that's deep in general, and is, of course, something that showed up in network theory everywhere, which is there's something about the nature of the potential connections in these populations and the way they would grow as you add elements to them. And if we think of them as lattices or arrays, the dimensionality becomes essential. All right, so the reason you had to hear that story is I want you to think about what I told you. There's a model that's the foundations of a major branch of physics. It was given to a graduate student by his professor. The student, I'm sorry to say, actually didn't get the fundamental insight because he only did it in one dimension. But what does history call the model? It's not called, well, occasionally it's called the Ising-Lenz model, but it's almost always called the Ising model. So what's the advice that we give all graduate students? Listen to every word of your dissertation or your master's thesis advisor, because who knows, it could immortalize you. Okay, so the reason I want to spend a little time on this is that you can see that this is what I mean that mathematics has something intrinsically interesting And of course, the fact that there's a qualitative difference in property of a one-dimensional and two-dimensional system, there's some cases in math where that happens. Random walks, for example, are recurrent in 2 dimensions, not recurrent in 3. But in this case, there was something as it's social sciences that's interesting to us. And that is the density of the paths between elements of a population is fundamental to understanding the collective dependence in the system. And that gives us some insight now as to how, if we specify social structures, what sort of conditions would be conducive to multiple equilibria. In other words, populations tipping towards one type of behavior or another. And the reason I wanted to emphasize this as a discussion is that it isn't just a matter of saying, oh, there are these really cool models in probability theory, and we're going to relabel the axes and call them social science models. It's rather that there's phenomena, the ideas, properties of the systems that are suggestive of what we would look for in socioeconomic environments. So, these models have been around for a while. The earliest use I'm aware of in economics is Hans Vollmer in 1974. And what he wanted to do was ask the following question. So you have actually he had an Erodigbro economy, and he was looking at aggregate demand, excess aggregate demand functions. And he wanted to know, suppose there's just idiosyncratic shocks to everybody in this population. Under what circumstances would excess demand functions be unaffected by their presence? In other words, he wanted to know if idiosyncratic risk somehow became irrelevant for aggregate behavior here. And so his argument was that if we thought about the preference shocks in this population as having a probability structure that was the Ising model, you could give an example in which you had idiosyncratic shocks. In other words, there's no common shock that just immediately move the whole system, but they could be collectively dependent enough that the excess aggregate demand function could shake. Okay, so and I mention that because this really is the first example, and I think this event doesn't get the attention it deserves. Another example is Beth Allen, who in 1982 applied this to thinking about the diffusion of innovations. So what she did was she again took an Ising model, in which you either have adopted technology you haven't. That's the binary analog to spin. She fixed this into a time, into an intertemporal environment, and the trick basically was at each point in time, each agent chose one technology or another, depending on what the neighbors of the agent were doing. And what she was able to do was to model the dynamics of technology choice. Now, I should say in parallel at this time, Shlomo, Alan Kerman, and others they initially brought in random graphs into economic contexts, and that's an example of what I'm calling social structure formation. And so that's kind of where the progenitors are of the more recent literature. So let me just give you some kind of sloppy math. In other words, I want to tell you intuitively what the key ideas are going to be, and then I want to give a real economic model. All right. So when I talk about the statistical mechanics models, obviously, as social scientists, we're not interested in the physics per se. That's irrelevant. We're interested in tools that let us characterize the aggregate behavior of populations of agents. That's the guts of what we want. And as I said, we also would like these characterizations to have the property that they immediately can be taken to data. And that's what I meant. I characterize a population with a joint probability statement. I can then take it to data because that joint probability statement is going to depend on parameters, which will be estimable. Now, of course, that's a little bit question-begging because one has to prove that they're identified. But it turns out in these environments, identification is generically holds. All right, so with that as the background, when I talk about statistical mechanics model, all I mean by that is population of objects. You call them atoms, you think of them as agents, what have you, and I want to characterize stuff about the joint probabilities of them. And so in thinking about them, the notation you see, at least in my papers, there'll be some omega A, and A is the index, is going to be the index set. And what the objective of the thought experiment is to start with conditional probabilities on the omega a's given the rest of the system. That'll be omega minus a. And from that, make some statement about the nature of the joint probabilities. That's the whole story. And I exhibit, I have a couple of typos, A's and I's are gotten a bit mixed up there. All right, and so again, the thought experiment, and I'm sorry I mixed up my A's and my I's, is that when you specify the mathematical model, you specify conditional probabilities. When you specify a socioeconomic model, that is not where you start. In a socioeconomic model, you start by saying this is the decision, or this is the way in which something happens. People graduate or do not graduate high school is determined by some process. And that process embeds the substantive socioeconomic assumptions you're going to make. If I say to you that if omega is whether I graduated from high school or not, if you say to me whether my parents graduated matters, that has to go on the conditional probability. Okay, so the reason I emphasize this is that there's a literature in physics called econophysics, which also tries to use these models in economics. And there's a literature on so-called complex systems economics. And that tends to ignore the gap between decision problems, conditional probabilities, and joint probabilities. It starts with the conditional probabilities. And that's actually not a good way to do economic theory. It turns out, for example, that some of the, and the reason for that is it's often not the case that the conditional probabilities have rigorous micro-foundations. And so in that sense, the model's incoherent. So that's why I'm pushing. You've got to start with the problem. All right. So that's the objective. That's what you start with, and that's the thing that we want to compute from it. And so an example in game theory where this has been applied is work by Larry Bloom, a paper called The Statistical Mechanics of Strategic Interactions. And what he did was he followed exactly this logic. He said that I'm going to start off, he's a good evolutionary game theorist. Agents aren't myopic, they're just sort of sitting there doing one thing or another. They're evolving through time. And when they are updating their behaviors, they look around at what their neighbor's doing and they behave in a corresponding fashion. And what he was able to show was a socioeconomically interesting idea. And that is that in a population in which you have people arrayed, let's say in this classroom, I compare the rate of diffusion, changes in behavior when people only interact locally versus the case where you react to the average of the whole population. Transitions are much slower via local interactions. And that's a general idea that's important in thinking about communication, maybe even thinking about some of the work you're doing, though I don't want to press the analogy too hard. All right, so I've talked in kind of a static language. In other words, I have conditional probabilities. I can think of joint probabilities. One can also embed these models. This is a common mathematical procedure in dynamic environments in which essentially each point in time, there's some mechanism for determining the times at which each of the elements updates, and then the updating is basically determined by the configuration at that point in time. And that's what I described as the Bloom example. And all that does is it says something of the form of the conditional probability that an element of the system has changed at time t in the arbitrarily small time increment is a function of what the system looked like at that point in time. And so writing down these kinds of continuous equations doesn't do anything interesting. All right, and so the point is that you can have continuous time models in which you have populations of agents evolving. That becomes kind of a natural index, since after all, I said one of the special cases that's interesting is 2 dimensions of a lattice versus 1 dimension. We can think of one of the dimensions as time, and the other dimension or 2 dimensions is space and the like. And so that's the way you would write it. Okay, so I referred to it the important caveat, and that was the importance of writing down the micro-foundations in order to reduce the conditional probabilities. And so there's an interesting paper by Ulrich Holst and Jose Schenkman that actually showed the following. Suppose I had a population, and the way that it works is your payoff is higher if the 4 nearest neighbors are doing the same thing. It's increasing the number of nearest neighbors doing the common actions, either 1 or -1. What is the conditional probability of his behavior given everybody else in the population? It's not the equivalent to the conditional probability of the 4 nearest neighbors. You actually have to go out 1 more. So it's the nearest 8 neighbors. Why? Because in equilibrium, there's an interdependence there, and therefore this guy, even though he doesn't directly affect his payoff, is useful in constructing the conditional probability. And that sort of isolates the distinction. In other words, what are going to be our intuitions for the interdependences? Some sort of complementarity or the like in preferences, in constraints, or in beliefs. So I'm going to embed them in the micro problem. When I wrote down his payoff function, I said it depended on 4 other people. The conditional probability is not just immediately derivable from that. The conditional probability is conditional on the rest of the system. What is the probability it does something? It's a predictive object. And therefore, even though this guy didn't happen to come into play in your payoff function, this one was relevant for prediction. All right. So let me point out an essential math trick, which you've probably all seen before, which shows up throughout this literature. And it's, by the way, one of the reasons that even though in statistical mechanics and the physics models, one is invoking an extremely large number of objects, or qualitatively different economics, but it doesn't matter for us. And that's the following. It is often the case in analyzing these models that, to be honest, they're analytically intractable. They're extraordinarily complicated objects. And even the Ising model in 3 dimensions does not have has virtually no analytical results. And that's after a century of sparse people on the planet working on these things. An extremely important approximation that exists in physics, which mathematicians, I would say, feel some unease about, but is useful, is the mean field approximation. The trick's the following. It's one thing to say that I set up an environment in which I express to you the conditional probability of your behavior given others in the system. If I replace that with the conditional probability of your behavior, conditioned not on the actual behaviors of others, but the expected behaviors, you can see that's an overwhelming simplification, because what it does is it converts this interdependent probability system into independent random variables. And we know how to work with those. Those are easy to average and calculate things. And the important idea is that in these populations, is a mathematical object, the qualitative features of these probability systems are preserved in the mean field approximations. And so understanding what is multiple equilibrium like, often the mean field approximations is easier to work with, and it reveals something about the entire system. There's something even better for social scientists. And that is everybody with me? So one thing to say, I tell you the probability of how each agent behaves given the behavior of others. That's too hard to work out. So I'm going to replace it with the probability of each behavior where I don't condition on the realized, but on the expected values of the objects. That's a lot easier. The better thing is that for a social scientist, those aren't the same model for substantive reasons. For the physicist, they're not the same model because one's simply an approximation of the other. But there actually are different theoretical commitments for a social scientist. It's a difference between a Bayes equilibrium, a Nash equilibrium, and a Bayes-Nash equilibrium. And this is an important point, that if I set up an environment in which people are making decisions and they can't observe what others are doing, of course the natural notion of a natural notion of equilibrium, I don't say it's uniquely natural, but a natural notion is to say that agents form beliefs about what they're doing, and it's based on those beliefs that they make choices. Now, of course, we can't just treat the beliefs of agents as this set of variables that are uncoupled from the rest of the system, because if that were the case, any behavior could be reconciled by suitable choices of the beliefs of the agents. There'd be nothing to say. And so the benchmark in economic theory is a certain form of rationality, and that's what the Bayes-Nash equilibrium says. It basically says, I have beliefs, I have an expected value for my neighbors that I use to make my decision. Well, those expected values better coincide with the expected values that are generated by the system collectively. So that simply says the benchline for the Bayes-Nash concept is a rational expectations equilibrium. That's just a restatement of what it means to be Bayes-Nash. But what's interesting is it turns out that in these environments, the Bayes-Nash equilibrium is the mean field approximation. Okay, and of course in many cases, I said to you, I think that people choose whether or not to smoke based on what their demographic group does. Probably not a bad idea to think about the Bayes-Nash. So, what I wanted you to see was this is a critical simplification of working with these models, but for us it also has a substantive interpretation. Now, it turns out that if you sort of think about what I've said, it's a population of objects. Okay, are you with me? And I think of them as having, there's conditional probabilities that describe one object in terms of the others. And many of these models, in fact, the interesting ones in some sense, all can be described as what are called Markov random fields. This is a straightforward generalization. It is a generalization of the notion of a Markov chain. So if you say, what's a Markov chain? I've got an index that's called time. That looks like a one-dimensional lattice from the way I drew it. And you just write probabilities that way. Okay, Markov random fields generalize that idea to account for interaction structures, which are going to be social network type relationships or adjacency matrices. And so the idea of a Markov random field is the following. I have this collection of objects indexed by A, and each object has associated with it something called a neighborhood. So my neighbors are going to be defined as some group of you, and they're going to have this very special property. My neighbors have the property that if you want to know the conditional probability I do something, and you condition on everybody else in the system, the only thing you need to know are my neighbors. Okay. So in other words, if the payoffs have the nearest neighbor feature, his neighborhood is going to consist of 8 agents. So why is this a nice generalization of Markov chain or Markov ideas? What are the neighborhoods in a Markov process? You have T has neighbors. T's neighbors are T minus 1 and T plus 1, so on and so forth. And so this allows the same Markov notion for arbitrary index sets and arbitrary types of dependence. The whole point of the Markov, what's a Markov chain? How do you start off by thinking about it? You said the probability of something at T given the entire history of the process, the only thing you need to know is T minus 1. It's the same thing that's going on here. But it isn't relying on one sided part of the Markov chain. And I made a quick comment, one-sided Markov, two-sided Markov can be conceptualized in equivalent fashions. But this does it for any structure of interactions. Now, that's a very general definition. The mathematics typically has been developed in the context primarily of binary valued random variables, which I index at 1, minus 1, and 1, and then kind of many of the results are associated with integer lattices. But here's kind of an interesting result, and that is, suppose I had a population of objects, and they're going to have they're going to be binary choices, or binary random variables. You smoke, you don't smoke. You stay in school, you don't stay in school. You get a PhD, you get how much you don't. All right? Is there some general functional form that would describe the joint probabilities of this collection of agents? And it turns out this was called the Hammersley-Clifford theorem. There is a general functional form, but it's going to depend on something that we're a little careful about, called a clique. So I don't know if this is what the Russian equivalent is. In American high schools, everybody hates cliques because those are the people that hang out with each other and exclude me. All right, so let's put it this way. How would I think about a clique? I would take the neighbors of each agent in this element in the system, and the cliques are defined as subsets of the population where everybody in the clique is a neighbor of everybody else. So in other words, my payoff depends on you, your payoff depended on me, or we're in a clique. And so what you can do is take the neighborhood structure and build up a clique structure. here's the big deal on the theorem. It turns out that the joint probabilities of this binary system, 1 minus 1, have a representation that is exponential. In other words, it must be the case that I can write the joint probabilities of the system as e to the following sum. The set of functions v of the whole system, where I sum over every click in the system. Now, and the key on these functions is each function, it only depends on the value of the indexed click. So there's some function that's short only, and that function's value, even though it takes as an argument the whole rest of the system, only depends on what we do, so on and so forth. Okay, so.
I'm sorry.
Yeah.
Is it true that the click is some isolated cluster of elements?
Yes, they're subsets of elements. And so I look at this, I know the neighborhood system, that's given. And then I form every possible subset of the population that has the property all members of a subset. This subset are neighbors of each other. So it only looks at mutual neighbors.
Do different clicks interact?
They can. So yes, there could be one click that's just the two of us. Then there's another click that's the three of us, as long as he's excluded. Okay. So you build up all the possible configurations. And so if you think about that, that's going to be important, because after all, we could be bosom buddies, so there's an intense interaction there. On the other hand, we all interact, but not with the same intensity, and so that's why you want to have distinct functions. Now this, you might say, why do I make a big deal about this abstract theorem? The answer is that we love it when we get the exponentials of things, because these factor, and hence you can work with them easily. And this is at least a statement that, in the abstract sense, working with exponential forms of these joint probabilities has a rigorous underlying justification. The sense in which it's less than meets the eye is those v's may be awfully complicated, so they're hard to work with. Okay, so that's. And by the way, I should mention, I hope this is not there's a very sad thing that 20th century mathematics developed a little bit. There's cases of parallel developments in the United States or in the West or whatever, and in the Soviet Union. And so many of these results don't exactly appear in the Russian mathematics literature, but things that are very close did years earlier. So the Adventisov had some theorems that were very close to this. And so it's kind of a sad thing that the mathematics communities were not in that rapid communication. Okay, so I've covered all that. And I'm going very poorly on time. So what I'm going to do now is give a real economics example. So I've talked in a very broad sense about, I could sort of think about decisions, and if people are making binary choices, here's some extremely abstract ways to think about the mathematical structure. I want to now make it very concrete. So this is a model that Brock and I developed, and the idea is going to be the following. Let's see, I'm going to skip all the way down. I'm going to generalize the model slightly. I'm going to say that rather than have two choices, there's L choices. They're going to be indexed 0 to the L minus 1. Okay, so the constraint set is nothing more than the alternate choices. So if it's an occupation, you're either a professor or a banker or a whatever. I just exhausted my family tree. Okay. Okay, so that's idea number one. Idea number two. Individuals they're going to maximize some payoff. And I'm going to think about the utility of the payoff as having, or the utility of the choice as having three components. The first component is HIL. So that's going to be an individual, that's me, the payoff I get that's fixed and specific to the choice. So if I like caramel better than chocolate, that's the payoff to that, relatively speaking. Okay, so each individual has a fundamental valuation for each of the choices. When I do econometric work, I replace the arbitrary HIL with a function of observables. And what's the trick in the econometrics? That replacement has to lower the dimensionality of where those HILs live in such a way that I can estimate the thing, or I can identify it. Second term is going to be the social interaction effect. And I'm going to take the Bayes-Nash view. I don't know, I want to eat ice cream flavors off. If I had hair, I would want it to be the same length as other males, right? I want to look, whatever's considered cool. And so the idea is that for each choice, I get utility if others are doing the same thing. So that's J multiplied by my belief about the probability of making that choice. All right, and then finally, I want this to have a structure that is respectful of unobserved heterogeneity, because after all, if I do econometrics and I have a model that fits perfectly, I've either cheated or I want a prize. Okay. So the serious point is, when it adds unobserved heterogeneity, that's epsilon. And so you can see what I mean now about conditional probabilities. I'm going to make a choice, and what is it I condition on? H and my expectation. And from the perspective of the analyst, that's the description of the data. All right, so we're going to make the standard assumption in multinomial models of a double negative exponential distribution. And the reason for that is, first of all, if I really wanted to push it, you saw there was some intuitive justification of Hammersley Clifford. I want to do it here, of course, because this is how we do multinomial logit in empirical work. And that was part of why I wanted you to see the Hammersley Clifford, because McFadden actually called it mother logit. In other words, that all these different models can, in some sense, be transformations of a logit model. All right, so if I condition on the beliefs of the agent, the constraints are just the different set integers up to L minus 1. I gave you my preferences. The tautology is the probability that I choose L given heterogeneity that's described by H, and my beliefs has to be equivalent to the probability that that choice generates the highest payoff of all of the choices. Okay, and that is a standard calculation. And that calculation basically says the following. It gives the canonical multinomial logit structure for discrete choice. In other words, the probability I do something is e to the beta. What is beta? That's measuring how fat the tails are for the epsilons. Okay? And if beta is very small, the tails are it's a little bit annoying. They're going to be very thin. If beta is very big, the tails are very narrow. Okay, and that matters. Obviously, if the tails were too big on the epsilons, or were sufficiently big, the probability of each choice has to be 1 upon L, because realizations of the epsilon would swamp everything else. So it's not surprising that showed up in the functional form. What's the second thing that is going to matter for my probabilities? Shock of shocks. How much utility I get from it in comparison to the other choices. Those are the H's, right? And then the third is going to be the social component, the intensity, J, with which I'm reacting to others doing the same thing, which is based on my P. So, I've essentially given you a mean field approximation to a statistical mechanics model. I had a group of elements. Each one had a discrete support. There are interdependencies, but they were mediated by expectations. So mathematics carried over perfectly. And the point is, it wasn't an approximation. It was actually what the information structure suggested should be the model. So this is like this kind of artistic way of saying so. Okay, the conditional probabilities are simply the product of the joints, the product of the conditionals, because of the way that I set the model up. And we're almost done. The final work is to say something about those beliefs about probabilities. As I said before, if I don't anchor those somehow, there's nothing to say. And so the baseline will be self-consistency or rationality, and what that means is nothing deeper than I want each probability, subjective probability, to coincide with the actual probability. And this is where I exploit the fact that in this system I have a set of non-identically distributed but independent random variables, and I know how to do expectations on that. I just integrate over the empirical measure for the H's. And so everything's nice and smooth. After all, probabilities induce probabilities. Given this probabilities, these are the actual probabilities. I look for a fixed point. The exponential has many happy features. One of them is nice and smooth, compact, usual, or not nice and smooth. And so since the support's compact, there's nothing to say. Immediately existence occurs. Now, and there's richer environments which Shlomo's worked on where symmetry can generally create potential games and generate the same thing. So I should have known more about that before I gave the talk, but I know about it now. Okay, so we're running very short on time. So I want to think about now the properties of this model. This basically is the description of the equilibrium. In other words, the only thing I had to figure out, the only hard work, is the notion, as it were, of the self-consistency. So what I have is a set of capital L probabilities P, and they are described by a set of nonlinear equations. Okay, existence was a triviality, but what's the question we like? How is uniqueness? Is there more than one set of probabilities? That would say there's more than one set of aggregate configurations generated by the same microstructure. So, how would I think about that? Well, the way I want to proceed is this is actually too hard to think about. And the reason is I need to restrict the density of the H's. Now, and what I mean by that is the uniqueness question depends on DFH, and therefore, since I don't tell you what it is, anything about it, I can never answer the question. So I'm going to take a baseline, which is extreme, but it's going to be informative. I'm going to assume every HIL is equal to some H bar. In other words, there is no differentiation of the deterministic private payoffs to the choices. So this is a world in which the only thing that differentiates one choice from another for me is how many others are doing it and that idiosyncratic shock. I'm just killing off one of the sources of heterogeneity. If we went back to wanted to do empirical work, that's not allowed. That would be a non-starter. But since the point of the theory, you want to understand properties of the model, this is a good simplification. And so in this special case, let's just think about it for a second. Let's suppose, okay, if H is a constant, there's no basis for differentiating, right? Three choices, so I might as well set H bar equal to 0. Suppose beta equals 0, so that the tails are arbitrarily thick. I claim there's a unique equilibrium, and the intuition is obvious. Beta small meant the tails are arbitrarily thick, therefore each individual choice must be 1 upon L, therefore the population collectively is 1 upon L. Those are the only equilibrium probabilities. Message, sufficient heterogeneity with respect to the unobserved heterogeneity in the thickness of tail sense kills off multiplicity. Here's another intuition. Suppose I just fix beta at a number, finite number, and I sent J off to infinity. Then I claim there has to be many equilibria. After all, if everybody makes choice 1, that's an equilibrium. Who would deviate? Because the utility loss is infinite. Similarly, if everybody chooses 2, that's an equilibrium. So on and so forth. Okay, without going into details, those will turn out to be the only stable equilibrium when you write down dynamic analogs of the model. But the intuitions we have now are the following, and that is heterogeneity somehow works against multiplicity. Large values of J works towards it. And you knew that had to be true, at least the second one, simply from the basic ideas of complementarity. When my decisions become my marginal payoffs become extremely sensitive to what you do, that correlates behaviors. And so, it turns out there's actually a theorem. Okay, and the theorem says that's really poorly written. I'm sorry about that. All right, so let's assume that all the H's are constants. The theorem says the following. I'm sorry that I wrote it that way. And that is that there will be at least 3 self-consistent choice probabilities, in other words, 3 vectors of those P's, if beta J divided by L is bigger than 1. So what is it saying intuitively? We fix L. What makes beta J bigger than 1, whatever that number is either beta's big or J's big. To say beta's big says there's little heterogeneity in the population. Hence, people are not leaning back and forth because of idiosyncratic shocks. The role of the social influence is correspondingly more important. The other thing that makes it big is J is large, and that basically says we're highly sensitive to what others are doing. Okay, now why is this scaling with respect to L? So in other words, if I fix beta and L, why would it matter what L is? Or beta and J, why does L matter? The way to think about it is the following, and that is in these models, these shocks are independent for each person. I'm getting draws from the same density for each of my potential choices. That means the more draws, of course, the more draws I have, the more likely it is I'm going to get one big one. What does a big draw do to me? It controls my behavior. And so the point is the following, that is the more draws there are, the more choices when they have this independence property, the more likely it is that individuals, a fraction of the population will have its choice become independent of whatever the social effects are, and there just won't be enough people left over to engage in self-consistent functioning one way or the other. And so the example I'd like to give is that if the choice was becoming an economist or a safecracker, and so there's a random shock that's called how good you are in economics, and then there's a random shock called how good how sensitive your fingers are. The point is, in the population, if everybody's draw either makes you a Kenneth Arrow or a, I don't know, a famous safecracker, or makes you a wonderful safecracker, it doesn't matter what the social interactions are. People are going to select based on the idiosyncratic shocks. Okay, and that's really all that's going on here. So, what's the upshot of this? This tells us many interesting things, I claim. First of all, it tells us that there's a very precise sense in which J, which is the index for complementarity between my choice and my beliefs about other choices, determines uniqueness versus multiplicity. And we have exactly the intuition we expect. Bigger is conducive to multiplicity. That's comment one. Comment two is something that's not so obvious, which is that the heterogeneity in the population either works against multiplicity. That's a good way of saying that if you have, if a population can't get concentrated with no role model, so to speak, then that works against the multiplicity. That's the second idea. And the third idea is the structure of choice in terms of the number of choices they all interact. Final comment, since I'm going to end at 6:15, is this model exhibits a property that's common in statistical mechanics models called a phase transition. So a phase transition, the idea is that you write down this probabilistic, this system, and obviously its properties depend on parameters. There'll be certain values of the parameters such that if the parameter is a little bit below it, you get one qualitative feature of the system. If it's a little bit above, you get a different qualitative feature. So you all know the most famous one. That's, of course, ice versus liquid water. 0 degrees centigrade, 32 degrees Fahrenheit. That's a phase transition point. In a ferromagnet, there's another phase transition point. Crudely speaking, that's how heat magnet is going to kill off the magnetization. Here, the point is you get exactly the same thing. There's a particular value which metrizes the interaction, the degree of heterogeneity, observed heterogeneity, and the degree of the intensity of social interactions, where if that product is above L, you get multiple equilibria. If it's below it, you get one equilibrium. Okay, so that's an important idea. That is that the qualitative property of systems can exhibit this type of tipping. Since I have 1 minute left, let me at least also comment, what happens if I introduce H? Non-trivial H. As I said, right now they're all set equal to the same value. What's going to be important, obviously, if the value is the same for every person, for every choice, it doesn't matter if I set it equal to 0 or a trillion. What's going to be critical is whether or not there's an imbalance across the H's. So suppose one of the H's, suppose H1, the first choice, is different than all the other H's. There'll be another phase transition, which is you start with multiple equilibria, and I start increasing the payout to one choice. Eventually, I'll kill off all the other equilibria. That's very intuitive. If the incentives to engage in a particular activity are strong enough, they will move enough people towards that activity that there aren't enough left over to engage in self-consistent function. So let me translate the algebraic remark into economic ideas. If I have a neighborhood or a community, and I'm worried that they're at a bad, at a bad equilibrium, in other words, the undesirable behavior dropping out of high school, what have you. One of the things I know, of course, is that the private incentives have to, the private incentives cannot be that strong to graduate from high school. And so what one has is, when we talk about something such as a poverty trap, or it's a term in the United States, the culture of poverty, in which you get behaviors in a community that are individually rational, but social, collectively are leading to bad outcomes, it isn't enough to either to engage in what is the stereotype of the liberal position, which is everything's because of lack of opportunity, or the conservative position, it's because people are not doing the right thing. In other words, the culture is somehow inadequate. It's the interplay of the social and private incentives that creates the poverty trap. So that this lack of nuance in the political discussion becomes evident when you actually think about the properties of this admittedly very abstract model. Okay, so I'm officially over time. What I wanted to, since you can't, control me, actually I'm going to skip all that. I want to say that I'm not going to cheat. Okay, that's actually the wrong talk. So, where the literature is, the final thing which we're working on in Wisconsin is how do I endogenize the social structure? So I can have a model in which first neighborhoods form, then choices are made, and of course, how did all the fathers and mothers in this room make choices on neighborhoods? We did them on the formation of the beliefs of the effects of the neighborhoods on the children. And that's a sequential multinomial logit problem. Stage one, we old guys and old ladies make a set of choices with respect to neighborhoods. Stage two, the kids will make a subsequent choice with respect to outcomes. And there's new properties that emerge from that. So let me stop there. Thank you.
Questions? Ответ бы получили.
Я, кажется, привел очень хорошую теорию, множество формул. Ну вот, скажем, была недавно международная конференция практических экономистов. Хоть какая-нибудь формула используется?
Да. Вот короткий ответ.
Ну, так она.
May I ask a question? You referred about the analogy of statistical mechanics in physics and some kind of studying of social systems. So as far as I know, in physics we have, for example, ferromagnets and other kind of systems, and we have the physical phenomena called spontaneous violation of symmetry. Mm-hmm. So it corresponds to the process which you described.
Yes.
And in physics we know about symmetries which are broken and restored after temperature rises. So do you know about say about some examples in economics and social science which symmetries we study and do you think about them?
I think that's a very important observation. And what I wanted to, the reason I jumped from to find what the Markov random field is to the example is that the example I wrote down, except for the fact that I have multiple choices, it literally is what's called the Curie-Weiss, the mean field approximation of the Curie-Weiss model in statistical mechanics. The Curie-Weiss model is a model of magnetization in which the probability of each atom spinning up or down is a function of the average spin in the system. And the multinomial analogy was the probability of one value is a function of the number of objects that are taking on the same value, and then because of the information assumption of the agents, the mean field approximation was the actual model for us. And the reason I want to pound on that is it's it's at least an example that says, starting with strictly economic reasoning, I didn't mention anything about conservation, any physical properties. There was enough in the economics to get a perfect map to a result in physics. And so what you've said is that there's much richer models about this than just this kind of atemporal, are you here or here? You can look at systems in which, let's take the H's. Let's private incentives fluctuate. And then you can ask, what are the associated dynamics of the system? Okay? And if we thought about that, you get into these very interesting questions such as, suppose that at the initial value of the private incentives there were multiple equilibria, but I was at, and this is the example I want to suggest is in the spirit of what you were saying. There's two equilibria, they're locally stable. That's what we'll have on those binary choices. I lower the private incentives so that this high equilibrium disappears, so there's not just a low equilibrium. What happens if I raise the incentive again? The problem is the following, that there was a bad equilibrium that was locally stable. It's not clear that when you write down the dynamic analog, you get a reversal.
So it is an analogy of two vacuum states, for example, in physics.
Yeah. And so, is everybody going to have this into it? I start out with a high equilibrium, low equilibrium. I kill off the incentives, so this is the only one that exists. If I restore the high incentives, it doesn't ensure that I jump up here. It may be because of some dependence in what we're doing. The restoration of the private incentives is not sufficient to move us to the desirable outcome. And so, that's the sense in which you see I can sort of work out some economic intuition, but you're going to know the relevant mathematical models. Another example where, and this is my understanding, is that this is a case where there are virtually very few analytical results. The models are just so complicated. There's something called spin classes. So the way that I talked about social interactions, as I said, there's a single parameter J that measures how dependent I am either on my neighbors or on everybody else, and the same parameter applied to you. A different formulation would have said, here's a population, and for every pair in the population, there's a unique value of the interaction. And so people who are my close friends have large J's, but somebody they hate, they have a negative J, so on and so forth. And so in physics, the idea is that you can set up systems in which you have JIJs that map all of the elements, and then you essentially assign a probability density to them. And the systems have extremely interesting properties, and very qualitatively different ones, possibly from the ones I've described. And what drives that difference is the presence of negative and positive J's. See, if the J's are always non-negative, even though the intensities are not there, we still have the potential idea. In other words, we're all kind of moving in the same direction. In other words, the complementarities are uniform. What happens if I'm assigning weights and some are positive or some are negative? So I want to be like you. You want to be like him. That's so positive J, IJ, positive J, IJ. He can't stand me. He wants to be the opposite. That's called in physics frustration. In life it's frustration. And that's a different type of system. And that's an interesting thing to think about when you have those, again, there's clearly, I gave a story as to how you would think about it in a social context. That has been completely unexplored in economics.
Okay, thank you very much.
What's implications to policy results from this project?
So policy implications that I would, they're at several levels. One is something I call it in one of my forays in philosophy, for better or worse, associational redistribution. And the idea is the following. When we think about redistribution, we typically think about money or stuff. And that's what a welfare system is. It taxes me and gives it to somebody who's less affluent. And the argument I wanted to make is that we take these social phenomena as first order to ameliorate inequality, it may be necessary to redistribute social structure or redistribute group memberships. Now, that shouldn't sound like an Orwellian 1984 thing. That's done all the time. An example I mentioned last night is the admissions rules for colleges, which are extremely contentious in the United States. They determine who gets access to these positions that we have good reason to believe have important payoffs associated with them. That's one example. A second example is, again, the United States is broken up into thousands of school districts. They generate about 40% of the revenue for the schools. And what's important, of course, is that if the rich are here and the poor are here, they generate different per capita expenditures. Well, the laws of physics didn't dictate the boundaries, did they, for those school districts? And so a question I could ask is, do I want to draw them differently? And in general, there's many policies that you could think of as efforts to redistribute who interacts with who. One of them is no deeper than how you draw the boundaries for individual schools within a district, or in principle, the school districts. Another example would be the rules for admissions or the matching of individuals. And those are certainly, I think, reasonable ways to ask policy questions. So, and I consider this, at least in my own mind, part of what I want the models to do is to say we ought to be thinking about these things. Now, to be clear, that isn't a prima facie argument that they ought to be implemented. So even if I could give you a definition of equality of opportunity that says do this because these are things a person is not responsible for, I can give you an example of affirmative action that nobody in the United States supports. If I wanted to eliminate racial inequality in one generation, in 2 generations, I could do it. I would require everybody to be married to somebody of a different ethnicity. It ends, right? Now, of course, you would all laugh at me and say that's the most monstrous thing imaginable. The point is that when we talk about the redistribution, I'm not going to ask what you're doing, so that's reasonable. The point's the following, and that is when we talk about these things, we're also dealing with 2 other factors that any ethical argument has to account for. One of them is personal autonomy, which we value, and that's why there's a non-starter for marriage. The second is that we don't think equality is a big only thing. Another one's self-realization. After all, do we take Andre Kolmogorov and ship him to that little school in Iowa because it would be equality enhancing in terms of the teaching of probability? You say no, because you want a person of genius to have been able to achieve that. And so those things have to be considered. So that's why I don't want to exaggerate some obvious things, but at least it puts these ideas on the table. The second issue is that it introduces worrisome questions about the ability to design policy under limited information. So if you think about the way I've been telling these stories, I said you could have a neighborhood or a community where there's high equilibrium for graduation, a low equilibrium for graduation. It's, a real bang for buck would be to pick neighborhoods which have 2 of these equilibria and somehow disrupt the low one and shift it back to the high end. Maybe even if I then get rid of the disruption, I stay there. Okay. That sounds like a wonderful thing to do, but that requires one heck of an extraordinary degree of precision in what we know about the parameters of the environment. And that then leads to, how do I think about policy in these highly nonlinear environments, which have things like phase transitions, but I don't actually know what the values are of the parameters. How do I do, what's the right way to think about the Bayesian decision problem, or maybe it's a mini-match where I don't even want to assign probabilities for the intervals around these things? Put differently, it could, one of the things that's neat about these models is all of the multiplicity, they were all collective phenomena. It was about the aggregates. For each individual, there's a well-posed decision. So there's no kind of uniform mechanistic thing about multiple equilibria. They emerge, as it were, as a property of the whole environment. So I could estimate beta J with microdata, and Brock and I have papers that show that demonstrate the identification holds. But of course, in any empirical work, I'm going to have uncertainty, kind of a standard error around those things. Well, how do I think about the problem if there's a phase transition and the data don't discriminate between any of the values above or below? Now, the reason I focused on that, I told you a very special story. I said the data basically gave me don't let me discriminate between those. That basically is equivalent to saying if I had a uniform prior, I have a uniform posterior. Well, who says the uniform prior is the right one? And that's exactly where the Hansen-Sargent work on robustness comes from. This notion that, is that they look at cases where you don't know the economic model with certainty. You have a baseline model, in this case the true parameters, and you know something within an interval of the truth. That's the closest you can be. And then that's where new decision theory is being developed and where mini-max arguments are made. So I put more questions on the table, I have answers. Those are the sort of things I think are critical.
just wondered, I have no clue about the empirical literature, and so presumably people estimate these discrete choice models to understand why neighborhood segregation occurs or why neighborhood tipping occurs, and trying to uncover the underlying parameters, right? So what can you tell about specifically on whether these phenomena that I mentioned occur because of economic reasons, because of preference-based discrimination or preference-based affinity, like of people that are alike, and so on. So what are the stylized facts, let's say, that we know from this literature?
So in racial segregation, one of the stylized facts is a phenomenon called tipping, which Tom is showing a model that, and what it intuitively says in the data, if you look at American neighborhoods, there's kind of fluctuations in the fraction of the population that's African American. Communities seem to hit some sort of threshold where the fraction of African Americans is above 25% or some number, all the whites leave. And so what the data say is if I look at transition dynamics in neighborhoods, they exhibit deep nonlinearities like this and suddenly go like that. The literal tipping thing isn't quite what you see. So I think that that type of phenomenon is relatively well documented. Now, it's not clear what the source of the social interaction is. It's clear that the white neighborhood members don't wish to have black neighbors, but there's two reasons that can be true, or three reasons. One is taste-based prejudice. The second, which is going to sound, it could be self-fulfilling beliefs about property values. So it could be that I don't care about the color of my neighbors, but I'm convinced that other white people do, and therefore the property values are going to go down if more African Americans move in, and you can get this kind of a cascade there. The third is, and this I have a graduate student, this should be his job market paper, is whether or not there's stereotyping going on, so a type of statistical discrimination. And so the idea would be that African Americans, crime rate's higher than whites, and so if some guy moves in my neighborhood, I immediately ascribe to him the unconditional number for the population. Now that, of course, can be ridiculous, and then conditioned and all the other stuff, including the fact he chose to live in the neighborhood. But you can nevertheless see that you could generate in the spirit of statistical discrimination, types of tipping phenomena. And so the fact is there, the mechanism I don't think is so clear. That would be one example. A different question could be, where is evidence of peer effects particularly strong? It's a contentious area because there are very serious defects in most of the empirical work. I don't want to be obnoxious, but it's unfortunately true. There has not been sufficient attention to various aspects of the identification problem. The phenomenon where I think the evidence is strongest is, not surprisingly, as I mentioned last night, cigarette smoking. One reason is simply that efforts by the government to collect data have been, the U.S. government spent billions of dollars trying to combat cigarette smoking, and so they did things such as go into high schools and interview every person to see who's friends with smokers, etc. So there's unusually rich data, it's the Ad Health data set, which is now often used for social network analysis. And so the data are extremely strong in terms of analyzing these things. Also in terms of the heterogeneity across regions, across ethnic groups, across gender, all that. It's so strong that I think that it gives a prima facie case. Now, that's not identification proof, but at the end, you have evidence, you make a judgment, and my judgment is collectively literature is very strong in that matter. There's other cases that trivially I could say are overwhelming. And what I mean by that is there's many phenomena which we know are entirely socially determined. And the best example is language. There's a reason why I don't know how to speak Russian. Even though at the age of 3, I'm sure that I was equally capable of learning it as a typical 3-year-old in the Federation. And so and of course, Chomsky's view of language says something about the nature of how the human brain is structured, and then we know lots of things about when plasticity declines. So that's all completely socially determined. and make the, however, you have to comment on something which is controversial, which is, when I said it was purely social, that's a pure war. In other words, when people say that the hypothesis is false, the argument is that every language is equally capable of communicating all ideas, subject to having the vocabulary added to it. And if that's the case, then it kind of says it's social, end of discussion. But there's evolutionary reasons why language should not be used to extrapolate. And it's actually improperly been used to extrapolate to argue parents don't affect children. It's a serious argument by some psychologists.
Okay, let's go. If you want to ask me, we can ask an official here after. Let's close the official part of the
Okay.